In this video, I'm going to introduce to you the ideas in valence shell electron pair repulsion theory, also known as VSEPR theory, or just VSEPR. VSEPR theory helps us predict the shapes of polyatomic ions or molecules, and it's really based on the idea of Coulomb's law. And what you do is you look at the electron pairs, either whether they be lone pairs or bond pairs, and what you do is you think of them surrounding your atom, your central atom in a molecule, and you think of these things as trying to get as far away from each other as possible, just like electrons tend to do in Coulomb's law. Electrons have same charge, and so those bond pairs, the electrons in the bond pairs or the electrons in the lone pairs, those are just going to try to get as far apart from each other as possible. A helpful idea when using VSEPR theory is the notion of steric number. Steric number is going to help us predict the way that these electron pairs are going to orient themselves to try to get away from each other. And the steric number, basically you just sum up the number of atoms connected to your atom of interest and the number of lone pairs. So if we write it as an equation, S, the steric number, is X plus E, where X is the number of atoms that are going to be attached to the atom that you're interested in, and E is going to be the number of lone pairs attached to the atom that you're interested in. So if we look over here at the chlorine molecule, Cl2, and we'll pick this particular chlorine atom over here. If I was going to calculate the steric number for this particular chlorine atom, I would recognize it is attached to one other atom, so X is equal to 1. And that chlorine atom has 3 lone pairs, and because of this, I would calculate that chlorine atom to have a steric number of 4. 3 plus 1 is 4. Let's go down here to this phosphorus atom in phosphate. In this case, the steric number S is going to be equal to X, the number of atoms connected to our phosphorus, which is 4, plus the number of lone pairs. I see no lone pairs on the phosphorus, so that's going to get a 0. So the steric number of the phosphorus is going to be 4. Let's take this particular atom over here on the left of the phosphorus, this oxygen atom, and calculate the steric number for it. If I was going to calculate the steric number for that oxygen atom, I would say, well, it's connected to one other atom. That would be the phosphorus, so X is 1. I also would recognize that it has 2 lone pairs, one on top and one below. And so I would calculate the steric number for this oxygen atom on phosphate to be 3. The other oxygens, however, we would calculate a steric number of 4 for those, because all of those are attached to one other atom, the phosphorus, but they all have 3 lone pairs. So the other 3 oxygen atoms would have a steric number of 4, in contrast to the oxygen that's doubly bonded to the phosphorus, which has a steric number of 3. The carbons in these 2 species over here, OCN minus and carbon dioxide, in both of those cases, the carbon is going to have a steric number of 2 because both carbons are attached to 2 other atoms, but they have no lone pairs. We're going to use this animation here to look at the shapes or geometries that result from structures with various steric numbers. To simplify our discussion at first, we're only going to focus on structures that have bonded atoms and no lone pairs. We'll discuss more complex situations in another video. Let's start with carbon dioxide. The carbon atom in carbon dioxide has 2 oxygen atoms attached and no lone pairs, and therefore it has a steric number of 2. With a steric number of 2, the bond pairs point at opposite directions so they can get as far away from each other as they can. 2 things pointing in opposite directions make a line, so we say the bond pairs take on a linear geometry. The oxygen atoms lie in a straight line with the central carbon atom. This means that the oxygen-carbon-oxygen bond angle is 180 degrees, such as you see here. Now let's move to a steric number of 3. For this, we'll look at boron trihydride. We know that boron trihydride has a steric number of 3 because it has 3 atoms attached to a central boron atom and no lone pairs. In the animation here, the boron atom is purple and the hydrogen atoms are white. Look at the way the bond pairs repel each other. They best repel each other by taking on what is called a trigonal planar geometry. What this means is that each bond pair points to the corners of an equilateral triangle. Here, all 4 atoms in boron trihydride lie in the same plane. Each hydrogen atom lies at the corner of an equilateral triangle, while the boron lies in the center of the equilateral triangle. Because everything lies in the same triangular plane, this geometry is called trigonal planar. Notice that the hydrogen-boron-hydrogen bond angles are all 120 degrees. Let's use methane as our model for a steric number of 4. I'll add another atom. Methane has a steric number of 4 because it has 4 atoms attached to a central carbon atom. In this case, the central carbon atom is represented by the purple sphere and the white spheres represent carbon atoms. In this case, the bond pairs best repel each other by taking on a tetrahedral geometry. And you're looking at a tetrahedral geometry here. Each hydrogen atom ends up being located at the corner of what is known as a tetrahedron. In this case, the hydrogen-carbon-hydrogen bond angles are all 109.5 degrees, which is known as the tetrahedral angle. We're going to use phosphorus pentachloride, or PCl5, as our model for a molecule with a steric number of 5. In this case, the bond pairs end up pointing toward the corners of what's known as a trigonal bipyramid. This geometry is best described by noting that the bonded atoms are located at 2 different types of positions. These locations are called axial or equatorial. You can think of these positions as being similar to locations on the poles or equator of the Earth. The equatorial positions are located at the corners of an equilateral triangle. Thus, these positions all lie at 120 degrees from each other. The axial positions point straight up and straight down from the center atom, 180 degrees from each other. Notice that the bond angle from an equatorial atom to the central atom to an equatorial atom is 120 degrees, but the bond angle from an axial position to the central atom to an equatorial position is 90 degrees. We'll add one more atom to get a steric number of 6. In this case, the bond pairs take on what is called an octahedral geometry. Sulfur hexafluoride, or SF6, is a molecule that takes on this geometry. In this case, it's pretty easy to see the structure because all 6 terminal atoms occupy identical positions at the corner of an octahedron. All bond angles are 90 degrees. Please recognize that this is only an introductory presentation of VSEPR, and that only geometries of chemical entities with no lone pairs have been evaluated. We'll cover the situation of structures that have lone pairs in another video.